Last time we talked about a binary search tree, okay, and then we briefly discuss with Boyd. And the binary search tree, let's actually review a little bit of the binary search tree. So basically, you build a tree, and then you have say 5, and then 3, and then 2, and then 4, and then 7, okay, and then 6, and then 8. So binary search tree, actually right side is always bigger than yours, left side is smaller than yours. But basically these are the key value, okay? Each node has a key value, and you can also store a string as its value. You can store a string. Okay, so basically this tree you can key and value, key and value. So tree can be used as the tree map. Okay, and tree map, when it is used, compared with the regular map, hash table or hash map, the searching time is order of log n. Okay, and but worst case you may have order n case if you are just one direction, right? You actually, the first one you add in is the smallest one, and you keep adding to the right side, and then you will end up with order n. Okay, so this is the tree map. And if you don't have a string value, then it can be a tree set. Okay, so tree map or tree set is just either you store a key or key value pair. Okay, that actually is the difference between map and tree, map and set. Okay, and then the main difference between tree map and the regular hash map is that in hash map you sacrifice the memory for performance. Okay, and then tree map is more saving spaces. Okay. So basically, tree by itself is a topic that related to the map. Usually, is the applications like that. But in fact, when we talk about tree, there are 3 types of a tree. One is data tree. Data tree is that you actually build a binary search tree. That is a data tree. You can also build a trie. Later we will talk about trie. Okay, T-R-I-E. Okay, trie is that you actually have a node. That's this is a root node, and then your branches you have the A, B, C, D up to Z. Okay, for the first letter, and then in A you may branch out as A, B, C, D. So you actually end up with each one is A, B, A, B, A, C, okay, whatever, something like that, okay? So your tree burn out every time with a different second next letter, okay? So if you go to the try and you stop at B, okay, let's assume you go just have one letter and B, you will stop right here. But if you have a BA, then you go down to the next node with A. So right here, you stop, you actually have B. If you go down, that has a BA. That's called try. Okay, that's called try. So you have the binary search tree, try, okay, and then there are other kind of a tree. This is data tree. Besides data tree, you have the so-called evaluation tree. So typical evaluation tree is your min-max tree. Okay, min-max tree means that you evaluate your tic-tac-toe game. So here you put a circle here, and next one you may have circle and then cross right here. You may have circle and cross right here. You may have circle and cross right here. So basically, if you are a player for circle, then you want to have a maximum score right here. And your opponents is cross, so you will have minimum point for your opponent. So min max, min max, min max, min max, you actually build up your evaluation tree. This is second kind of a tree. Okay, it's called evaluation tree. So we build a data tree. Binary search tree is one kind of a the so-called data tree. Trie is also a data tree. Okay, and then min-max tree is evaluation tree. Another type of tree is just like the Fibonacci tree. It actually is recursive call tree. F of 5 calling F of 4, F of 4 and F of 3. Okay. Okay, anyway, whatever people call it. This kind of tree is called recursive call tree. Okay, so when we talk about different tree, they are of different kind of a purpose: evaluation tree, recursive call tree, and data tree. So in competitive programming, I would say most of the time we are dealing with the recursive tree. Okay, when you deal with a file and the data structure, then you are dealing more with data tree. Okay, when you are writing an AI program or you are playing a chess, automatic chess, then you will do min-max tree. Okay, but in this textbook that we are using, there is no evaluation tree or the so-called recursive call tree. Okay, this one is purely only on the data tree only. Okay, this chapter A is only on data tree. So we will talk about some other tree today. We finished the basic binary heap. Okay, this binary heap we also talk about it in Java already. And here is also had a binary search tree. So today we are going to finish the last section that's on the balanced binary search tree. Okay, and then we will talk about a little bit on trie and a little bit on the recursive call tree, different tree. Then we will finish this tree part, and then we will move on to the graph part. And the graph part, there are many algorithms, and I would say most of the competitive programming is in this chapter 9 only. Okay, this is more important chapter if you go to the goal division of the user code. Okay, so basically they seldom test you on the balance tree. Those kind of tree actually seldom tested. They may test you on the recursive call tree, yes, but building the data tree actually is too big. Okay, it's actually too big. So before we go to the balance tree, let's actually work on trie first. Let's work on something called trie. Okay, this trie is not on the textbook, but let's look at the trie. Okay, let's look at trie tutorial. So before we, this one is a so-called a prefix tree. Okay, trie data structure is a prefix tree. It's also a kind of dictionary or used for map. Okay, it's also used for map. And the searching time, because actually the branch of the tree is 26. You are from root and you go for A, and then A go for A, B, A, C, okay, AA, okay, whatever. So the branch vector is 26. Every node has 26 child. So actually the depth is shorter compared to the regular tree. And better, and also this one trie is better used for when your key is a string. It's more efficient than when your key is using integer, when you use for trie. So it's actually some kind of a dictionary tree for the trie. Is that okay so far? Yeah. And it's not in the textbook. So in the textbook, you cannot see anything related to trie. Okay, so but we want to learn about trie, okay? It's actually very important data structure. So basically you have a root node and you have A and D. Okay, sometimes this trie you can actually, because you want to save space, so you only have the branches for the existing dictionary. So you have a A, okay, and then after A you have A, N, D, and A, N, T, right? It's a two word that is in there. There's another word that's actually D, A, D, and then D, O. So this one totally just four different words. So this different word, they actually step right here. Sometimes you are only A, if you A stop there, you may also store some data right here. So this can also work as a deep node because sometimes you have the A as a single word, okay, in the dictionary. But right here, we are storing four words in there, but it's organized such a tree. And this trie, so far, the branch vector is only when you have data in there. So usually when we do trie, each node you have a node, and then the childs you can use a vector or a radius for it, and then each node it will have its value, and then its key. Eventually you have a key. So right now it's root, and the next one is A, and then you have different child. Okay, something like that. And the child usually is a radius. You can use a radius. And maximum would be 26, but minimum maybe only 1 or even 0, okay? Like this one, it had 0 child. It had 0 child means actually it's a lead, okay? Is that okay? Hello?
Yeah.
So this is the trie, and then how you organize it. So you need to know about what is the trie data structure and what is the need for it, and then compare with the hash table, okay, these different things. Let's look at what is the trie. So trie, as we talk about, is a tree structure, and then it actually go on with the prefix ABC, okay, prefix, and it actually is a dictionary. So you go by the keys ABC value. So it's more suitable for a tree, and then it can be compared with hash table. Hash table again will waste memory because you actually hash the string to certain location. Sometimes they have collision, okay. This trie actually you don't have collision. It actually is a tree based. Okay, so basically the advantage of this one is efficiently when you do prefix search later by later. This one is faster. Okay. And then we can easily print over in alphabetical order. So the data is well ordered in alphabetical order. There's no need to do sorting because your word is going like this. It's actually just do depth first searching. It will go by alphabetical order. Okay, that's a question about it. And then the searching time order log 26 of N, okay, because actually branch vector is 26. Does that make sense?
Yeah.
So that actually is not log 2N, it's log 26N, so the performance is better sometimes, okay? No overhead for hash function, no collision, that's good thing about it. But hash table do have order of 1 such time, okay? So it actually is a order of L. L is the number of word in the query string. Okay, that's actually its time. So property, okay, this one I think it's okay. This one is using alphabet, whatever, okay. Then the data structure like this, we talked about it already. This is a trie. So from 0 to 26, you can store the children using the array list, okay? So you line up like this, that's your child, okay? But because you can actually use the array list, so some of them may be missing. may be missing. Okay, you can also use an array. Use array, then you are also wasting your memory. So to use an array or to use a vector, that depends on how much word you have. If you just loaded a whole dictionary into it, then I would think using array is better because guarantee most of the node you are using it. If you just have limited dictionary, then you probably prefer to use a vector. Okay. Okay, whatever. This one is not hard. So every time it goes down to a level. So this one is not hard. So let's look at C double plus. So you have a trie node and then you have a dictionary. So that's actually copy. Okay. Let's build it. Okay. Using the example they have right here to use the trie. So here I'm going to open a folder and put it in our data structure course. This one, CPP, we are going to go for lecture 9. The main topic is called balance tree. Okay, so we are going to go for balance tree, but first I will create a subdirectory, this one called trie. Okay. So this trie, let's actually put on a trie, use this folder. Let's create a file called trie node, like H. Okay, let's put it over here. So, this is a structure and then the children is using array, okay? And then the word count, we put 0, okay? At this moment, we put 0. Let's try node. So let's do if undefined, okay? Try node H, okay? Then define try node H, okay? And then here, and if. Okay, and then there is a constant called alphabet size. So let's do integer alphabet size. So this alphabet size, because that right now we are using A to Z, okay? And sometimes you actually alphabet underline size. What's wrong with it? Let's see. Okay, this one is a triangle. How comes it actually must have a constant value? So let's put constant. Okay. So this one is a try node.h. Okay, so this is a try node, and then you will have insert, search, and delete function in your data structure. Okay, so let's see this one. Let's directly using the C double plus. Okay, if you have a try node and you put a key and you are going to do insert, okay, you're going to do insert. And then you have the try node. Let's see. So these are just a try node, but it actually is a C type of function, okay? But let's just copy it, okay? Just copy it and then let's put it over here. Okay, so this one we have a insert key. Okay, so this one we need to use string type. Okay, so we have an insert key. We have try node. We have a function called insert key. And then there's a child node. This child node is you have a root, and then child node is a current node, and this one there is a children alphabet. So this one actually, this right here is using the children, but the algorithm use a child node. Let me check, okay? Someone need to be changed. So this one is actually it's called child node. Let's use the children, okay, instead. Let's use children instead. This one, identifier is on, okay, this one we need to do using namespace std here, okay? In order to make it work. So here, that's using the children instead of child node, okay? Let's call it children. I'm sorry, I would prefer child node, okay? Since child node is more used, children is less used. So let's put here as child node. Okay, so it's a structure, and then you have an insert key. Let's copy the other algorithm in as well, and then let's discuss it, okay? So we have the searching, you have key, you have a node and you search key. So here, this one, copy, okay. Right here, search key, okay. Okay. So this is search function called prefix exist or not, okay. You have to keep for it, and then you want to see, okay, that's good. Next one, let's actually have let's have searching. Oh, that one is wrong actually. Okay, let me copy it. Let me copy the right version to it. Okay. So this one. Now this is a C double cross version already, so it's okay. So let's actually move on to the next one. Next one is the search key. Wait. So there is a function called is prefix exists or not. Then next one is the search key. Let us copy this search key as well. So put this search key over here. Okay. And then let's move on to this one. Deletion. Okay, let's do deletion. So deletion. C double cross. Let's copy this one. So that has the delete key. Okay, that's okay up to here. And then let's go back to here, implement data structure. So I think actually they do have a complete version over here. with try node, search key, delete key, and main function. So let's do this. Okay, let's do this. Let's do this. I make a mistake. Let's do this. Let's actually copy the complete version. Let's copy this one. Okay. Let's put this. Okay, copy this whole file. Let me redo it. Okay, let me redo it. So this portion actually up to here. Let me actually put it over here. Okay, the whole thing before the end. Let me pass it one more time. But the main function, let me actually main function. Let's cut it. Okay, cut it. Cut the main function. Okay, I'm sorry. Let me cut main function out. Okay, one moment. So cut this main function out. Okay, and I'm going to put it into test try.cpp. Okay, this one called test try.cpp. Let me put it over here. Okay. Okay, this is test try over here, and then on top of it, I need to include IO string include string and then include this one is try node.h using name space HTTP. Okay, this portion is to include a try node.h. So right here, this one. Okay, we have the delete key. We have the search key. We have insert key. We have a try insert key. We have a try node. So try node right here. You have children node of 26. Word count, and you have a constructor. This constructor will initialize all the children to be null. That's the initial value. Okay. Now this one is a constructor. So now if you insert a root and you have a key, you set your current node to be the root. So from your root, you actually for each character in the key, you actually go to current node the child for that one, if not null, or if you equal null, if you equal null, you need to create a new node, right? You create a new node, and then your child should be inserted to there, okay? And then your current node move on to the child node and continue to the next key until you finish the whole key. Okay, this one is insert. So this insert is okay. You basically starting from your root, and then you search for your, let's assume it's A, you go for your A node. And then if this A node right now is null, there is no such a thing, then you create a new node and then put the new node there, and then you will move on your current to this location. Okay. If you already has it, you keep going down, and then until you actually reach the node that you want to have. Is that okay so far? For the insert, is that okay so far?
Yeah.
Okay, so this insert is very simple. pretty much you use the key and then go down the node one by one, one by one, one by one. Okay, go down to the next level. So search key, you get the same key. You get started from your root as well. Okay, and then for each key value, if the node is actually null, because right now you already built up the tree, but if the node right now you search for a certain letter and that letter is null, then you raise false, return false. That means that it's not in there. The search key failed. You actually return the fail false. Otherwise, you keep doing it. Okay, you keep doing it, and if you actually finish it, then you return your you actually keep going down to the child node until you finish everything. If you finish everything, it's not this, then you look at the choose current node's work count greater than 0, then that it will return true there. So work count means like word count means that how many words have been used right there. Initially it's 0. When you do insert, there's no change. Okay, that's when you do insert, the current node word count will increase. So word count means that you come to here. If you put a B, okay, so you go A and B, and then you count from 0 increase to 1. Okay, so next time if your AB come again, it will increase to 2. So basically, this word count and the key is just like your what your word versus the frequency. So this word count is its frequency. Is that okay so far?
Yeah.
Okay, word count is a frequency. So word count is frequency, and then if it is greater than 0, that means that your key is in there. So when you delete it, then you go down the same path again, and then if you cannot finish the path, then that node not in the tree, so far not in the tree, you return false. Otherwise, it will decrease the word count. Otherwise, if you already has it's not null, then you will delete your word count. Okay, your counted number would be decreased. And if your count equals 0, you actually count equals 1. That means what? Your count equals 1. That means you have the last case. Then you would delete it and set your child to be null. Okay, that's what you would do. Whatever. That's branch node. Okay. Not equal null. You will actually set it to null. Then you are done. You will go back. Okay. Delete this. So this one is the delete algorithm. Okay. Then let's go to the main function. So the main function actually using the try, and then you insert this different word into it, and you check in the size. You have the input string, and then you go to the input string and insert every word into it. And then you want to check these 3 words, and then you do for loop to check word one by one. And then you delete these 2 words. Okay, so that's what the main function is working. Okay, so this one, let's try. Let's do save. Let's go to terminal. Let's do G++. It's called test try SCBPHOS try. And test try. Okay, it actually just worked. So this one, I just want to give you the idea of what is a trie and then give you a simple code to make sure you understand what is trie. It's actually quite simple, okay? But only one thing I would like to talk about is that right here is using array. You can also use array list or vector for it. Okay, you can use a vector for it. Then you will save some space. So when you use a vector for it, you basically say if you are A to E, then you should go 0, 1, 2, 3, 4. And then if you are trying to search it for 7, it's more than the size of your vector. That means you are not there. If you are smaller than that, then you may check if it is null or not. So maybe 2, but you don't have the C yet. You don't have C. Then you will store a null over there. Okay, so that's the way if you use a vector for it. Any questions so far?
No.
No? Okay, let me send you these 2 files. So in a way, trie is a replacement for your map, hash map as well, okay? So we started with the hash map because it's quite important. It's a quite important data structure, okay? So now we actually give you the test trie. And also trie node. Okay. So that's actually a dictionary tree using trie. Okay. Next one. So that one we don't discuss balance or unbalanced because it's by the dictionary. Okay, it's by the dictionary. Now next one we are going to talk about the balanced tree or unbalanced tree. Okay. So that's AVL tree. Okay. So basically, we talk about binary search tree, and binary search tree may not be balanced. So right here, our topic changed to balanced tree. Okay. So before we go for the balanced tree, let's look at this the reason for it. That's because that you have get and put into the tree, and this tree is invented by 2 gentlemen, Adelson, Velsky, and the Landis. Okay, these 2 people. So AVL tree. So AVL tree is a tree for the name of the 2 people. Okay. And anyway, this is a balanced binary tree. Okay, balanced binary tree, you need to know about balance factor. Balance factor is based on your right tree's height and the left tree's height. So when it's well balanced, these 2 things is 0. When it is greater than 0, then your left tree is deeper. If your left value is less than 0, then this one, the right tree is depth of 3, left tree is 1. So you actually end up balance factor of -2. So when your tree is well balanced, it actually is close to 0 or close to 1. That actually is a beta balance tree. Okay, so we use a balance factor using the depth of the tree. Is that okay so far? Okay. So then you may have different tree. You have only one letter, A 0 time, you say A. You add a B, then you have a child of A. And then you have a C, you actually become like this, and D, okay? So you actually build up your tree like this, okay? So this one is left heavy tree. Your left side always be heavier, okay? This is left heavy tree. Okay, so basically, looking the number of the total tree node, actually, the height 0 is 1 node, okay? And the tree of the height 1 is 1 plus 1 full node, okay? And tree of the height 2 is 1 plus 1 plus 2 equals 4. Okay. So more generally, your height n is 1 plus the height n, actually n minus 1, h minus 1, and h minus 2. Okay, so basically this one, your height 1 is 1 plus 1. Height 2 is actually 4. Let's see. Total number of the node in the tree. Height 0 is 1 node. Height 1 is 2 node. Height 2 I think this one is 3 node, 1 plus 1. Either this one is, oh, I mean, sorry, it actually is talking about complete tree. Complete tree is like this. Okay. So when we talk about the high tree, complete tree right here is actually totally a 7. Okay. So high levels tree is 1 plus this plus is similar to the Fibonacci number. Okay, whatever. This one just do mathematical analysis, whatever. Okay. Okay, then we look into the implementation. So basically, this one you need to put some data into the tree. Okay. And then in 12, you need to do update balance. Okay, you need to do update balance. We'll talk about how to update balance right here later. Okay. And then you would, okay, basically, unbalanced tree is that if you are heavily right, you would do rotate left to be balanced. Okay, that's the technique. If you are unbalanced to the right, if you are unbalanced in different way, that's if you are unbalanced in this way, you will rotate right to make it like this. Okay, so to make a tree balance, you basically using the rotate right and rotate left to make it balanced. Okay, to make it balanced. So like this tree, this is heavily like this. So you will use this one to do rotation. You use this one to do rotation. So your C is keep there, right? So your C is right there. C is your node. So your E and your D will merge together, become the right tree. So basically your E right here, your D original is the right tree for E, it become the left tree for E. Okay. And then we create that subtree like this and then put under C. Okay, that's the rotation. Anyway, this is rotation to maintain balance. So here there's a rotate left and they should also have a rotate right algorithm. Okay. And then there's a overall rebalance algorithm. So this one, because there's no main program, so let's also look at this AVL tree from the peak. Okay. So it is one kind of a binary search tree. So originally you need to set up your binary tree like last week. Okay, there's a binary tree. And then there's a balance vector. You need to calculate your balance vector. So there's a balanced vector algorithm. You need to always keep track of your balance vector on your tree. Okay, you check every node to see your left child and right child, whether they are balanced or not. okay? Okay, so there is a searching, deletion, and insertion. Okay, basically, searching is the same as the normal binary search tree. There's no problem. Insertion, you insert, and then you want to make sure that the balance vector of the impacting node is less than or equal to 1 after insertion. So after insertion, your balance vector or the node that you insert to should be less than or equal to 1. So that actually, at most, one child is more heavier a little bit, okay? So you keep track of that, your tree will be balanced. So this insertion need to insert to actually ensure it, okay? Deletion the same. Deletion, you also, when you delete one node, you also need to make sure your children that you affected is within 1, okay? So this is rotate left, okay, rotate left. This is rotate right, okay. Okay, so this one, you may also have this one. This is a CAB case, okay. So you move down your A that become like this, you do this AB to make it like this, and then you rebalance. This is left right rotation. So it add another one called left right rotation, okay. When you have this pattern happen, okay. Then you move up B, drop A, and then rotate C to the right. It's left right rotation, okay. So there's a left right rotation. There's also right left rotation as well. So there are totally 4 kind of rotation. Okay. So an advantage of this AVL tree is that it's self-balanced. Okay. Every time you insert or delete, you maintain the balance. And then disadvantage of it is that you have more difficult to implement. Okay. More difficult to implement. And running time higher. Okay. Then we have an insertion algorithm. Okay, this one actually B14. So here you have a node and you have left child and right child, okay? And then you do have the right rotation, okay? And you have a height measurement with the height function, okay? And this one, okay, anyway. And you also have a left rotation and then get balance vector, okay, get balance vector. And then you do have an insert right here, okay? Okay, let's look at this one, this insert program, okay? So here I'm going to open a new folder. This one, let's create a new folder called AVL, okay? In the AVL, we create a new file, this one called AVL insert.cpp, okay? And let's put a code right here. Okay, so this one, basically you have a node for it, okay? And that is binary tree, and each node has a key and a height value, okay? And also you set it. And every time you can get the height, okay? Or you do rotation, rotate right rotation. Right rotation teach you how to do right rotation. So basically you have a node called Y, okay? And then Y has a left. And then this one is also called X. X has a right one that's called T2, okay? Okay, so we are going to do a right rotation. So you said this actually is a swap algorithm, okay? So your X right, you put your Y into there, okay? Your X right, you put the Y into there. And then your Y's left, put in the T2. Wait, this one is actually this one is actually let's look at it more carefully. So you have an X node, and then you have Y node. This one is right rotation. Right rotation is rotating like this. So you have Y node, you have also Y's left. Okay, so this one is your condition. You want to do rotation. Okay. No, this one I think I need to look at this one is okay. A subtree rooted at the Y, okay, it's rooted at the Y. Then Y's left is called X, okay. And then X right is called T2, okay. And then X right set to Y, so you assign your Y to here, and Y's left, you assign the T2 here. So you put this one on here. A little bizarre, actually. Let's look at the rotate left. So you have an X node. X node is rooted. And your Y is right. And Y's left is called T2. So Y's left, put the X over there. And then X the right, put in your T2. T2 is originally your Y's left. Okay. Let me see, this actually is a little bit bizarre. Okay, let's look at this one. So rotate right, you have No. Let's move up. The first case is left rotation. Left rotation, assuming you are rotating this one, you basically, this side you no change. You actually move this one to here, and you assign this node to here. Okay, that's the left rotation. So this one is rotating root. This is root node. Okay. So this root node, this right child need to be assigned to here. Okay, right child being assigned to here, and this whole thing need to be assigned to Y. Okay, I think that's the purpose you would do this. That's the purpose you would do this kind of the left rotation. Okay, the whole purpose is to what I'm talking about, and then you adjust your X and Y's height. Okay, the data that you have already changed. Okay, and your left rotation is similar, and then you get your balance for the node. So when you do insert, if the current node is null, then you create a new node and you return. That's your the node that you want to have. And then if key less than it, you insert to the left side. Key greater than it, you actually insert to the right side. Okay, that's the recursive code. And then you get your balanced. If you are not balanced, then you check your left case. Your balance greater than 1, and then your key is less than your left key. Key less than your left key is like you are unbalanced. And then your key and your left key is bigger. Then this one you will demote and then move this one up. That's actually is a right rotation. So here analyze the left, right, left, and left, right, different cases when you do different rotation. Okay. And then at the end, you perform a pre-order traversal. Then you print out your tree in the pre-order vector. Okay. So let's run it first. So this one only insertion, there's no deletion. Okay. So Trie plus AVL insert, that's DDDHO AVL insert. And then we run AVL insert. You get the data in the pre-order. Okay. So that's C. You do insert 10, 20. So this one is really solid. So in case you would actually keep adding to the right, it would be adding to the right. But after your traversal, you are 30 over 20, and then you have 10 and 25. This one you have 40 and then 50. So that's the resulting tree you have based on the pre-order. Is that okay? So far? You are supposed to get a very tilted tree like this. But in fact, your pre-order is a tree like this. Is that okay? This is AVL tree. Okay. Any questions so far? So to study some data structure like this, you just go through the data structure and then look at the different functions, try to understand how to rotate right, rotate left, rotate left, right, rotate right, left, how they are performed. That's it. That's everything you need to know. The theory is not hard, difficult. It's just you need to understand what they are really doing. Okay. Let's go back. And real implementation aside, just emphasize one more time, actually AVL tree seldom happen on the competition because this one usually take a long time to implement the tree by itself. So that's not a purpose for the competition. Okay, so here we have another one that's deletion that will show you how rebalance is done after some node is deleted. Okay. Anyway, let's put this code right here. This one called AVL. Okay, I do not use the textbook because textbook do not have the main function. Do not have the main function, and then we cannot test it. This one the same. You actually look in the node. You look into the node. Okay, the node structure, and then height function, rotate right function, rotate left function, get balance. And then when you do insert, you call those different functions. And now when you do mean value for the node, and you do deletion, you will do deletion, and then after that you do balance. Okay. So this one, let's create a new terminal. And plus AVL delete. Okay, so AVL tree try this different data structure basically is when you need to build a data structure to store your searching tree to save time and save space, then you build the tree. Okay, there are also other tree like here called red black tree. Okay. Red black tree, this one not in the textbook, but red black tree, when you do job interview, red black tree is openly tested problem. Okay, red black tree is always openly being tested. So this one is another type of a balanced tree, and they do also have the insertion, deletion, and searching. So the red black tree, you do have a tree, you have a 4 and then 2, 6, and then 1, 3, 5, 8, and then 7. So this is black, red, and black and red. Okay. So first, let's look at what is the red black tree. So red black tree is also another type of the self-balanced searching tree. It's different from the AVL tree. Okay. And then each node is colored as the red or black. Okay. And the primary objective of this tree is to maintain the balance after insertion and deletion. So because you have the red and black color on the node, you pretty much know about your height. Okay, you don't, if you balance your red and black, you pretty much should have pretty balanced tree. So red black tree has a no color, and the root color is black. Red color cannot have the red children, must have the black children. Every pass from the node to the descendant to null node had the same number of back node. Okay, so every pass you go would have the same number of the black node. Okay, that's the black property. And the lead property, all the lead nodes are black. So these are the property of the red and black. And based on the balance of red and black, you get your tree balanced. Okay, that's the whole theory. So the property ensure the longest path from the root to any leaf node has no more than twice as long as the shortest path. Okay, so you have the some path, but your shortest path and your longest path will not be more than half, more than twice. So this is the way they maintain the balance. So your longest short searching time and the shortest searching time is within a factor of 2. So left side is a red, is a black, and this like this, okay. And then it's still a binary search tree, so you do know this. So right here, you have this. This is incorrect red black tree. This one is the correct one. So you have black, and your red must be interleaved with black. You cannot allow the red right away. Okay, that's the red black tree. So red black tree again, it actually guarantee the order of n searching time and insertion time. Okay, so it give you all of them order of n. So when you compare with AVL tree and red black tree, actually AVL tree are more balanced than red black tree, but they may cause more rotation because you do rotation all the time. And red black tree do not do so many rotation. So how does the red black tree ensure balance? A simple example of understanding the balance is that the chain of the 3 node is not possibly red black tree. So it's impossible you have a red, you must have these 3 left, 3 black, that's actually not okay. You must have a black like this, okay. This one is not okay. You will put this one over here to make 2 red. So there are certain property you cannot allow them to happen. This different property right here. Number 4, each pass has the same number of a black. So this one violated 4 because this one you have 2 black, this one you have none. So you cannot allow it to happen. So you will make it like this or make it like this. Either way, that your red black tree will work. Okay. So this one you have consecutive red, that's wrong. This one you have 2 black here, 1 no black here, that's also wrong. You have to alternative. You cannot have 3 black in a row. Okay, then it's actually next one is to look at how you insert data to maintain the red black property. So it has the insertion, searching, deletion, and rotation. So they talk about how is the rule for insertion and how is the rule for searching, what is the rule for deletion, and how you do rotation. Okay. And then anyway, this one same thing as copy the code over. And let's look at the code. So key point when you study this kind of data structure is you go over the data structure and then you need to fully understand in what case you do red coloring and in what case you do black coloring and in what case you need to do insertion. Okay. So the tree itself is like that. You have a node, and each node you have the color as well. Okay, so when you get started, you have data, you color it to be red. Okay, that's constructor. Always color to be red. Then you build a red black tree. You do rotation and change color for it, right rotation, change color for it. Okay. And you can fix insert. When that's comparing your color of your parents and your child, making sure that you don't violate the rule, and then you do rotation when it can help you to avoid the violation of the 4 different principles. Okay, so here it has an algorithm how those rotation being done. Okay, anyway. It has a detail, so when you trace the code, you need to know about how the rule for black and white, black and red need to be done. But otherwise, if you look at the rotation, it right here, it did not tell you really deeply how the rotation be done. It all give you the how the right rotation will be done, but why this can maintain the principle of the 4 principles, they don't tell you. Okay, they don't tell you. They just tell you what the right rotation need to be done. So when you study it, you also need to remember these. Okay, you also need to remember how the rotation being done. But as for why, they don't tell you. They just tell that. They just tell you like the 4 rules that they want to maintain. Okay, so this red black tree is there's a technical paper you can search internet if you are interested in why they do this. So you can do red black tree application. If you're really interested in the red black tree, you should go for the Wikipedia and search for the original documentation for red black tree. Okay, there's a ton of theory, but it actually tell you how it works. Okay, I think there are a lot of operation that you can look at it, but the theory is a lot of theory anyway. I cannot finish it right here. Okay, really a lot of theory after the red black tree. You see, there's just so many pages. Anyway. This one, let's do it. This is also another balance tree. It's called G dot class. Yeah. Black CPP HO red black. Okay, whatever. We actually made a code work. Okay. If you need a theory, you do need to study it more carefully. This part, as I said, it actually is just providing you the implementation of different tree, okay, different tree, and then theoretically is a lot of theory behind it. These actually are some publications, some PhD dissertation before, okay. But in terms of how to use them, you just need to know about the basic code and how the rotation being done. So when you study, you just need to understand them, okay. And then there are a lot of theory behind it. So, but red black tree, AVL tree, and the balanced binary search tree. These are typical data structure. When people study data structure, you need to learn all of these, even though the chance for you to use it is not that high. But usually when you do interview, they are the interview topics. Okay. Okay, anyway. You just remember your red one cannot go two node in a row. Okay. You have to do balanced, and using the balanced rules, they will guarantee that the longest path and shortest path is less than half. Okay. That's the way that they maintain their balance. But AVL tree, in terms of balance, is more balanced than red black tree. Red black tree is just you can call them the so-called what heuristic algorithm. Yeah, you can call it a heuristic. Okay, red black tree is a heuristic. They just tell you you should do this, but they don't guarantee it is optimal when you do balance. It is not optimal. Okay, AVL is more balanced. So this one is just a heuristic. So when heuristic happen, it's very difficult to discuss why the heuristic should do this, because there's no theory behind it. Okay, you can say that there's a long history of the theory behind it, but in fact, there's no guarantee why people need to do it. Okay, so this laboratory is something like that. Okay, any questions so far?
No.
So right here, actually, when you look at the comparison for this different map, you can use a sorted array. Put is order of n because you need to move your data around. Get, you can do binary search. Okay. So insertion the same. Okay. And then hash table is always order of one, but you will waste your memory. Binary search tree, worst case is order of n. AVL tree is log n. Okay, so these are the basic comparison. Okay, so we finish this tree chapter. Next one, we are moving on to the graphics. Okay, and graphic is the most important chapter in terms of data structures. Okay. In fact, when you go to UC Irvine do have a course in called graph algorithm. So graph algorithm by itself is a college course. Okay, it is a college course. So right here, we do not intend it to actually teach as much as this course. So we may spend another 4 or 5 weeks, basically go over the basic graphic problems. Okay, that's our purpose. We'll go through that, and then basically we started with the definition of graph, adjacent matrix, adjacent list, and then this different problem over the graph. Okay, these are different algorithms, many different algorithms, and all of these are testable in user code. Okay, user code silver and above, they all like to work on these different problems. Okay, they don't do tree, but they do a lot of graph or two-dimension map. Okay, any question?
No.
No, that's actually get started for the graph part. Okay, the initial part, and then we are going to close today. Okay. So basically, graph is a general case for tree. Tree is a graph without cycle. Okay, graph can have cycle. Graph can have direction, and graph may not have direction. And graph can also be bidirectional. So have the direction bidirectional and may have no direction. So graph is more complicated than tree. Okay. Okay. And a good graph and bad graph would determine your algorithm a lot. Okay. So that's also another thing that actually need to know. So you need to learn when and how the graph need to be used and how you can implement it. You use a adjacent matrix or you use a adjacent list that totally make the implementation quite different. Okay. Okay, anyway. So you need to learn about what is vertex. Vertex is the node. Okay. Edge is the connection from one node to node. So this edge can have a direction, can be bidirection, can be no direction. Okay. So it's a directed graph or digraph or no graph. Okay, or no direction graph. And then each node or each edge may have weight. On graph, the major difference is that you may have weight. So you may have such weight. So 1, 3, and 2, okay, and 4. So you may have a problem called minimum spanning tree to have a spanning tree that cover every node. That's one problem, minimum spanning tree. You may have the shortest distance problem, okay? You may have shortest cut problem. So your node and your edge may have weight in your graph. Okay, edge may have weight and the node may also have weight. And then you sometimes need to evaluate your graph based on the weight. Okay, so that's the basic of this graph. Graph is conceptually a mass model. Okay, a mass model that is. So a path is from one node to another node. So when you have direction, then you cannot go this way. That's wrong. You have to go this way, this way. That's a path. So this is not a path because this one actually reverse the direction. Okay, a cycle is that when your graph have a cycle like this, that's a cycle. Okay, that's a cycle. When you travel from one node and back to its cell, in the middle you travel to other node, then we call it a cycle. Okay. So graph is a abstract data type, and then data structure, you use a metric or you use a vector to implement it. Okay, so that's the data structure. It is an abstract data type. So you can have a constructor called graph to create the object. You will have the edge vertex, edge, get vertex, get edge. Okay. These different functions that you can use. And then you have two ways you can implement your graph. One is called adjacent metric. Adjacent metric means that you have node 0, 1, 2, 3, 4, 5. Okay. So node 0 connect with node 4. Node 4 connect with 3 and 5. Node 1 connect with node 0. Node 2 connect with node 1. And node 2 also connect with node 5. And node 3 connect with node 2. And node 4 connect with 4 and 5. And node 5 connect with 0 and 3. Okay, so you actually will build a graph like this. Okay, you can, this one actually is a directional, so that actually you can clean up one more time. So your 0 go to 4. Let's assume this is from, this is 2. Okay, so 0 go to 4 with weight of 1. And then 1 go to 0. So 1 go to 0 with a weight of 5. 2 go to 1 with weight of 4. 5 go to 2 go to 5 with weight of 1. 3 go to 2. 3, let's put 3 over here. 3 go to 2 with weight of 9. 4 go to 3 with weight of 7. And go to 5 with weight of 8. 5 go to node 0 with weight of 2. 5 go to 3 with weight of 3. Okay, that's the overall graph. So you actually, this one is a directed graph, only one side, okay. And then you put the weight on it, you will get this. So computer doesn't know the graph, computer know about the metric, okay. Computer know about it. The metric, same thing, they have one problem is that if you build a JSON metric, then you may waste your memory because many nodes may not have the edge on it, then you are wasting your memory, okay? But it's faster in terms of implementation, okay? And you can also implement it as a list. So each vertex has its own neighbors. Neighbor is a list. Okay, you put your neighbor list on as a list on your graph, okay? Okay, they are implementation. So today we don't go into the implementation. Let's save it for next time, okay? So today we just go over the basic graphic idea. Next time we'll go to the vertex and then do two kind of implementation, including the using the table and using the vector, okay? Any questions so far? Okay, that's it for today, okay? See you next time.
Bye, thank you.
Bye-bye.